So this video is about giving you practice with an integral like this, where you are going to have to use partial fractions to calculate the integral. So have a go with pen and paper, and then afterwards come back and look at the solution. See you in a few minutes. Okay, welcome back. Let's look at the solution on the next slide. So on this slide, I want to calculate this integral. And what we're going to do is to expand the integrand in terms of partial fractions. So to make life look simpler, let's completely forget about the integral and just look at the integrand. So it is a proper rational function, 1 divided by this polynomial. If you expand it, it's a polynomial. And I'm going to write it, therefore, as a constant whose value I don't yet know, divided by x, plus another unknown constant divided by x minus 2, and a third unknown constant divided by x minus 3. And what we want to do is to find out what are the values of a, b, and c that make this work for all values of x. So each of these three factors is a linear factor. It is linear in x and it vanishes for some value of x. This would vanish when x is 0, this would vanish when x is 2, this would vanish when x is 3. And this is the general structure of a partial fraction decomposition for an integrand like this, or a structure like this, where we only have linear factors in the denominator and they are only to the power of 1. They're not repeated. It's not like x minus 2 is all squared or anything. Okay, so to find out what a, b, and c are, what we're going to do is put them together over a common denominator, and that common denominator is going to be the denominator of the original integrand structure. So, if we have a over x and we want to put it over this denominator, that's easy. It's a times x minus 2 times x minus 3 all over x, x minus 2, x minus 3. You can see that would cancel with that would cancel with that, and we'd be left with a over x. And then we add similarly b, this other unknown constant. Now this has x minus 2 in the denominator. Doesn't have these factors, so what we're doing is just multiplying top and bottom by x. So we have it here, they would cancel, and by x minus 3 they would also cancel, and you see that this structure is exactly the same as that. And then we have plus c, and here we multiply by these two terms, x and x minus 2. Again, they would cancel and we would be left with c over x minus 3. So this is just an algebraic rewriting, and what we've done is we've written it in such a way that this decomposition now clearly has the same denominator. And that's something we must always see in partial fraction decompositions. So what we want to do now is we're going to say if this is equal to this, the denominators are already the same, it must be that the numerators are identical. So this is equal to 1 for all values of x. So what we're trying to do is to find the values of a, b, and c such that all of the quadratic terms in x squared that you're going to get when you expand this, they all have to vanish. All of the terms linear in x, proportional to 1 power of x, they've all got to vanish. And the constant terms have got to be equal to 1. So we're going to have 3 equations for 3 unknowns. So what we're doing is we're equating the coefficients. So it's helpful just to write something like x squared there to remind us. So how many powers of x squared are there here on the right? Well, you could have a times x, that's the only way of getting x squared here, so that's a of them, plus b times x is bx squared, plus c x times x, so that's a c. So it's a plus b plus c, the sum of these three unknown coefficients must vanish, because otherwise you would have quadratic terms in x and they cannot be there because they're not on this side of the equation. We do the same thing now for x. There are no x's here. They're going to have to vanish. And on this side, you could have x times minus 3 and x times minus 2. So that's minus 5 times a. That's the number of x's to the power of 1 from this term. From here, it's simpler. It's b times x times minus 3. So it's minus 3b times x. And here in the same way, it's c times minus 2 times x. So the number of x's in the numerators here is minus 5a, minus 3b, minus 2c. There are no x's here, so that combination must vanish. And I would also say we can easily multiply both sides by a minus sign. Minus naught is naught, it's not changed. But here we can just get rid of some of these minus signs, or all three of them make that plus, plus, plus. And then finally, if we look at the constant terms, this term and this term has a factor of x in each of them. So therefore there are no constant terms. The constant terms can only come here when you have a times minus 2 times minus 3. So that's plus 6a, and that's got to be equal to 1. So that tells us that a is equal to 1 over 6, and that is our first unknown coefficient. So now, what we can do is we can insert this value of a into this equation. So we have 1/6 plus b plus c is 0. And if we just rewrite that by taking the 1/6 to this side, we have b plus c is minus 1/6. So that's minus a minus 1/6. Similarly here, we'd have 3b plus 2c is minus 5 times a, so that is minus 5/6. And if we want to solve these two equations for the two unknowns, b and c, the easiest thing, I think, is let's just multiply this equation here, the top one, by 2. And if we do that, we're going to get 2b plus 2c is minus 2/6, which of course could be minus a third, but because down here we have sixths, I'll leave it as it stands. So now, let me just give these equations names. So I'll call this equation 1 and this equation 2. So equation 1 minus equation 2 is going to give us the following: 3b minus 2b, so that's going to give us b. And the c's are going to cancel. 2c minus 2c. That's why we multiplied this equation by 2, to get that cancellation. And then here we have minus 5/6, and now let's be careful, it is minus 2/6. So it's minus 5/6 plus 2/6, so we get minus 3/6. And that means that b is minus 1/2. And that's our second result. And now we can substitute into, let's say, equation 2 again. So from equation 2, we had originally, just look at the pink, b plus c is minus 1/6. So c is minus 1/6 minus b. So we have c is minus 1/6 minus b, and that's minus 1/6 minus minus, because b is minus 1/2, so it's minus 1/6 plus 3/6. And that means that c is 2/6 or 1/3. So that's our value of c. So now we have the values for all three of our coefficients, a, b, and c, and we can write out our partial fraction decomposition. And our partial fraction decomposition has the following form: 1 over x times x minus 2 times x minus 3 is equal to 1 over 6x plus, minus, because b is negative, a half, and that's times 1 over x minus 2, and then it is plus 1/3 times 1 over x minus 3. So that is our partial fraction decomposition, and on the next slide what I'm going to do is substitute this into our integrand and integrate it. So what's the key things that we've done? What are they? First of all, we made the partial fraction decomposition of the integrand, and because we've only got linear factors here and they're not repeated, then we just have 3 possible structures, 1 for each of these powers. And then we just put it on a common denominator, which by construction must be the same as this common denominator. And then we equated the numerators, so we forget about the denominators since they're the same, and we say, well, this must be true for all values of x. 1 has got to be equal to that, and that means you've got to have the same number of values of x squared, of x to the 1, and of constants. That gave us 3 equations, and then we just solved them, and this was our result. So let's integrate this on the next slide. So a moment ago we wrote down this result for the partial fraction decomposition, and what we do now is we substitute this into the integrand here. So we replace this by this. So we're going to have 3 separate integrals: 1/6 times the integral of 1 over x, minus a half, just pulling the numbers through the integral, times the integral of 1 over x minus 2, plus 1/3 times the integral of 1 over x minus 3. And these are all linear terms, and we can just write the answers down, they're logarithms. So it's the logarithm of x times the 1/6. If you differentiate it, you would get 1/6 times 1 over x. Perfect. Here we have minus a half times the log of modulus of x minus 2. If you differentiate that, you will get 1 over x minus 2 multiplied by the derivative of that, but that's just 1. So you would get this. And in the same way, here it's plus 1/3 times the logarithm of the modulus of x minus 3. So now you could leave it like that, but we can also try and put things together using the rules for logs. And to do that, what I'm going to do is I'm going to pull out a common factor of 1/6, open brackets, and then we have the logarithm of the modulus of x minus, and then it's 3 times the logarithm of the modulus of x minus 2, plus 2 times the logarithm of the modulus of x minus 3, close brackets, plus some integration constant. And all we've done here is said, for example, minus a half is minus 3/6. And now what we're going to do is use the rules for logs just to bring this into here as a power, bring this into here as a power. And what we get is 1/6 brackets the logarithm of mod x minus the logarithm of the modulus of x minus 2 cubed plus the logarithm of the modulus of x minus 3 squared, close brackets, plus some integration constant. I suppose we don't really need the modulus sign here because this is squared, but it doesn't hurt to write it down, and after all, if you were to take the 2 outside, you definitely need the modulus, so I'm going to leave it. Okay, so now we have the logarithm of this minus the logarithm of that, so we could just put that in the denominator, and then we're going to add the logarithm of this, so this will multiply, will come in the numerator. So what we're going to obtain is 1/6 the logarithm of the modulus of x times x minus 3 squared over x minus 2 cubed. Close the modulus, add an integration constant, and that is our result for this integral. And what I will do on the next slide is I will give you an exercise to practice combining logarithms like this. So here is the exercise. I'd like you to combine these 3 logarithms into one logarithm using the rules for logs. Have a go with pen and paper, come back in a few minutes after you've done it, and then I will talk about it a bit. Okay, welcome back. Let's have a look at it. So one of the first things to notice is that the coefficient of this log is different to the coefficients of the other logs. And the rules for logs are all of the form log A plus log B or log A minus log B. So they've got to have the same coefficients. So one of the first things that I would say you have to do is you've got to write y is the logarithm of the modulus of x squared minus the logarithm of 1 plus x minus the logarithm of 1 minus x. And now you can combine these in different ways. One way would be to say, well, this is the logarithm of the modulus of x squared, and both of these terms have got minus 1 multiplying them. So I could write that this is minus open brackets the logarithm of the modulus of 1 plus x plus the log of the modulus of 1 minus x. And then I can combine these terms as the logarithm of 1 plus x times 1 minus x. So in that way we're going to get equals logarithm of x squared minus the logarithm of the modulus of, and 1 plus x times 1 minus x is 1 minus x squared. And then we just use the rules for logs, and this is the logarithm of x squared over 1 minus x squared. So that's one way of doing it. A different way of doing it would be, well, not very different, but a little bit, would be to say, well, y is the logarithm of x squared, just as we had here. And then we're going to subtract, say, this term from this. So we're going to say minus the logarithm of 1 plus x minus the log of 1 minus x is equal to the logarithm of x squared over 1 plus x minus the logarithm of 1 minus x. And then we're going to say, okay, we're using the rules for logs, and that means that we are going to bring this coefficient, or this argument rather, into here. We're going to divide that by 1 minus x, and if we're dividing this by 1 minus x, what it means is we put 1 minus x in the denominator. So we obtain the logarithm of x squared over brackets 1 plus x all multiplied by 1 minus x, close the modulus, and then again we could just tidy that up by multiplying it out, and 1 plus x times 1 minus x is 1 minus x squared. The cross terms cancel. So we see that these two results are, of course, exactly the same. With that, I'll stop this video.